to go red. All right. So today we're lucky to have, actually, we're going to cut this off, but how do you pronounce your last name? I'm so sorry.
That's all right. Suau.
Suau.
Yeah.
All right. So today we're lucky to have Miguel Suau, who is a fourth-year PhD candidate at TU Delft, working with Frans Oliehoek and Matthias
Spahn. Yeah.
Spahn. His research focuses on designing scalable methods for multi-agent reinforcement learning. He's interested in partial observability, memory, and probabilistic graphical models. He's currently an intern at JP Morgan AI Research and has been an intern at Huawei and Unity. And this is kind of a follow-up talk to last week's seminar from Frans. So yeah, we're lucky to see the follow-up. So thanks very much for coming, and excited for the talk.
Yeah, thanks for inviting me. Well, I'm Miguel, and I'm going to talk about how to scale up multi-agent reinforcement learning using distributed simulators of large network systems. And like I said before, please stop me if you have any questions or if something is unclear. Just let me know. Okay, so this talk is based on two papers that we recently published. One is Influence Augmented Local Simulators, a scalable solution for fast deparallel in large network systems, and that was published at ICML this year. And the other is Distributed Influence Augmented Local Simulators for parallel multi-agent reinforcement learning in large network systems, and that's going to appear at NeurIPS this year as well. Okay, so to give you a bit of context, well, we all know that deparallel has very poor sample complexity, and so far it can only be applied successfully, at least that I know, through simulation. And of course, simulators of very large systems, if they are actually available, are usually very slow. So yeah, so our goal in this paper, or in these two papers, has been to try to build compact representations of these systems such that we can build simulators that are faster to run, and then we can speed up the whole learning process. So I'm going to start from the single agent perspective, and then we'll move into the multi-agent perspective. Okay, so when I talk about a network system, I'm basically meaning a system like the one here on the right, where you have certain components that are interacting with one another, but their interactions are structured in a certain way such that they only occur through a subset of the state variables, so a fraction of the state variables. And you will understand what I mean now when I explain more details. But so systems like the one in this figure, this is a traffic network with 25 intersections. This was designed, or I think it's one part of the flow package that Eugene worked on. So it's on the Sumo simulator, but there's a flow wrapper that you should definitely try if you're doing RL for Sumo that has this environment. So we just took it from there. So again, there are 25 intersections, and we're going to focus on trying to train an agent to control the traffic lights at the intersection in the middle. And basically, we're going to formulate this using the framework of local FPOMDPs. And this is just some extension of the ordinary POMDP. And the difference with it is that we have state factors. So the states are determined by a series of variables or state factors. And that's the factor in POMDP. And then local, because both our observations but also our rewards depend on local information. And in the case of the traffic example, that means that the agent can only observe the cars when they enter this blue dash box, and it's only rewarded for what occurs within this dash box as well. So there are a few reasons why you would like to model this task in this way. Why would you like? Why you would like to have like local observations and local rewards? But essentially, if you think about the local observations, well, if you're training a neural network that takes as input the entire global state, if this state is very large, that might be a bit hard, right? Because you have too many variables, most of which are irrelevant. So a much simpler task is to just focus on the local information that you are having an impact on. So you're giving away full observability for more manageable problem. And when it comes to the rewards, well, having a local reward facilitates credit assignment, because now you can just focus on like the reward only depends on the variables that you are really having an impact on. So if your reward depended on the rest of the state variables, then it will be very noisy and it will be hard to distill any information from it. Okay, let me know if something is unclear, but otherwise I'll just continue. Okay, so well, if we have both local observations and local rewards, why do we need to model the entire system? Why do we need to have a transition function that depends on the full set of state variables? Can we just condition our transitions on the local state variables? And well, in general, the answer is no, because these local state variables will be, in most cases, affected by the non-local state variables. And in general, we'll have to condition our transition function on the global state such that we can sample the next local state. So can we do something that is slightly in between, not just computing the transitions of the entire, like conditioning an entire global state and or conditioning on the local state? Can we do something in between? And the answer is yes. Well, we're gonna analyze this problem using this dynamic Bayesian network. And essentially what we see here is that we have two local variables, x1 and x2. This is just a prototype. Of course, the transition dynamics for the traffic simulator are a bit more complicated, but this is just an example. So it's just a local FPOMDP prototype, and we have x1 and x2 are our local variables. Then we have A. This is the action of the agent, and we see well how one variable affects the other in the next transition, the next time step. So as long as the picture looks like this, then we're okay, because this system is independent, and we can just build the local simulator and train our agent on top of it. But when the transition dynamics depend on the non-local state variables, when we have other non-local state factors affecting our local region, then that's not the case anymore, and we'll have to condition on the global state. But in this type of problems, the ones we're tackling with this method, there's a property that holds not just in the traffic simulator but also in many other network systems, which is that the local state variables are only influenced by a subset of the non-local state variables. So even though the entire system is in some way affecting our local region, it's only doing so through a small subset of variables. And you see here that I changed the variable from y to u, because now this variable is what we call the influencers, and essentially this influencers summarizes the information, summarizes the influence of the rest of the system on the local region. As long as we know the value of this variable, we don't need to condition on the rest of the global variables to compute the transitions. I'm going to pause here and Yeah, if you have any questions. So in the traffic example, these influence sources are essentially these 4 variables that we have here, which you can think of them as like binary variables that determine whether a car is going to enter at the next time step or not. And in the traffic simulator or in the traffic network, we know that even though the rest of the system, the rest of the network is affecting the local region in some way, it's only doing so through this 4 road segments that we see here in the image. So these are my influence sources. Any questions?
I have a question on the influence sources variable themselves. So you said they're binary, right?
This is just in this particular case. This is just how we modeled this problem. But in general, they could be continuous. They could be they could have more not just binary, but there could be more categories, like more. It could be discrete, but like more labels.
Yeah. All right, thank you.
Yeah. So of course, like in a more complicated traffic network, you will have maybe more lanes. So then you will need more variables as well. You will also have the velocities. Maybe that will be also part of your influence sources.
Yeah. I just kind of figured for something like whether a sub part of the environment influences another subpart environment, like that would be more of a like a continuous domain, right? So it's kind of like to me, I kind of compare it to like hard versus soft attention.
Yeah. I think that's a good analogy. Yeah. So yeah, in general, these variables could be continuous as well. Yeah.
Thank you.
But the important property that needs to hold is that the non-local variables affect the local variables through a small subset of them. Like a fraction of them are the ones that are directly influencing the local region. And this is not just the case of the traffic network, but another example could be a heating system. So imagine you need to control the heating of a room in a very large building. The rest of the building is influencing my room, maybe through the walls. So my walls, in a way, are the influence sources, and as long as I monitor the temperature, then I can forget about the rest of the building. So that's another example.
I have a quick question.
Yeah.
Can you model every? Can you model every multi-agent system this way?
No. Only systems that have this particular property, I think. I mean, probably maybe you could try to learn this influence sources in some way, and have like some sort of dynamic way of, because in other types of problems, the influence sources might change from one time step to another. So if you had some sort of model that could determine what the influence sources are at every time step, then you may be able to apply this to any multi-agent problem. But in principle, they need to have this particular structure.
I see. I have more questions in this vein, but I'll save them for the end of the talk.
Okay. Yeah. All right. Any more questions? Okay, I'll just continue then. Okay, so essentially now all I'm saying is that the non-local state variables are the local state variables are conditionally independent of the non-local state variables given the influence sources. So that's what we see here in this equation. As long as I condition on my influence sources, I can forget about the rest of the state variables. So ST here contains both XT and YT. YT were the non-local state variables. Okay, so the problem here is that I'm only so my transitions, I'm only sampling the local state variable. So given the current local state, the action, and the influence sources, I can sample the next local state. But I also need the influence sources at the next time step so that I can compute the next transition. So what we do is we have this distribution of the influence sources, this conditional distribution, which is conditioned on the local state action history denoted by L here. And the reason we can do this is because the agent can only perceive local information. So therefore, the agent will only be able to perceive this conditional distribution of the influence sources with respect to its own action observation history. So because of this, we can keep track of these influence sources by forming this sort of belief over the influence sources that depends on the local state action history. And this is the way. In this way, we can sample the next transition and based on the local state action history and the action. And again, this is because the agent can only perceive the local region. Okay, is this clear? This is sort of like one of the key points. We have a theorem as well in the paper where we show that we can bring this one step farther, and if my agent can only perceive, let's say, because like it has limited capacity or something, can only perceive a truncated history, then I only need to condition my influence model on a truncated local state action history. So the way I like to think of this is that you need to simulate the world to the level of detail that the agent will be capable of perceiving it. Yeah, it's a bit philosophical, but this is sort of the intuition. Okay, so now we have this influence distribution here. The problem is that due to combinatorial explosion, we cannot compute it exactly. So we can only try to approximate it from data, and this is what we do. We create a data set of local state action histories and the respective influencers, and then we optimize, say, a neural network using these cross entropy laws. Okay, how am I doing with time? I don't see.
It's 1:30, so you're
Okay.
Yeah.
All right, so so if we put everything together, then we have a local simulator and an approximate influence predictor, and that in many cases will be faster than trying to model the environment with a global simulator. So the combination of local simulator and approximate influence predictor should be faster to run. And this is actually the case in the two environments that we explore here. This is for the traffic domain with the 25 intersections. We have two baselines. We have a global simulator, and we have an untrained influence augmented local simulator. And this is essentially just a local simulator, but with an untrained influence predictor. And we see that an agent that is trained on that simulator performs very badly, whereas the agent that is trained in the true influence augmented, not in the true, in the influence augmented local simulator that is being trained, can match the performance of an agent that is trained on the global simulator. And this is important because our argument was that we couldn't just use the local simulator. So the gap between the blue and the red curve confirm that hypothesis or that argument. And then, of course, in total runtime, we see that we are much faster when we train on the influence augmented local simulator. Okay, now I'm gonna move on to the multi-agent version of this. So this is the new RIPS paper that we are gonna present in November, December. So if you have any questions from the other part, this is a good time.
Just a quick one reminder: is it a cooperative global reward, or are there local rewards?
It's cooperative because the task is cooperative. The fact that we use local rewards, it's just because first, like, it's easier for credit assignment, so that's just our choice, and also because we need it for the method. But I mean, you could also train a model that predicts the global reward based on your local state action history. So it's not it's an assumption, but it's not a very strong assumption.
Yeah, I guess I was, we could talk about this at the end, but I'm curious what happens if you do that piece.
Yeah, I think that might be actually beneficial, because then you avoid this problem of credit assignment, because you're only computing the global reward with respect to your local state action history, which means that you remove all the noise in some way. But in many cases, even though this local reward is going to be a bias from the global reward, it might be just good enough, and you can train very good policies with it. But it's true, like the agents could in some way start competing because they have different rewards, so it's not fully cooperative if you model the reward in this way.
Great, thank you.
Any more questions? Or
yeah, I have a question on the pre-distributed part. So previously I've seen work on factorizing like joint policies or factorizing joint value functions. So this is my first time seeing. I mean, I'm interpreting this as a factorization of the environment itself, right? And it seems like the only way to kind of introduce any kind of correlation between the like factors or like factored self-environment themselves is via this influence variable. And I mean, in this particular paper anyway, the variable itself is like it's a scalar thing, right?
Well, for us in this traffic domain, was just the binary variable, but
so binary variable, like, so would you kind of open question, I guess, but like, would you say like a scalar, binary, or continuous variable is enough information to?
Well, I mean, you can put as many variables here as you need, right?
Yeah.
So here in this Bayesian network, it is just one. But in the actual environment, we have 4 of them. In the warehouse environment, I think there were 20 of them. So I mean, you can put as many as you need, such that they capture this influence.
Yeah. And then do you get any kind of I don't know, like monotonicity guarantee, where it's like, if you get the optimal policy for one particular sub-environment, then once you combine them together, do you get like a global optimum?
You mean?
So like, if the agent reaches the best performance, like optimal performance within its factorized sub-environment, and then you do that for all environments, and then
I think we'll get
combine them all together.
We'll get to that when I talk about the multi-agent case, which is coming right now. But
gotcha.
But yeah, I hope I can address that question. I'm not sure exactly what you mean, but yeah, maybe as I continue, then you get your answer, hopefully.
Yeah, that's good.
All right. Okay. So now in this new paper, we were thinking, well, can we do this for all the local regions? Can we basically, so in the first slide I showed that we were just controlling one intersection. Can we do this with all the 25 intersections simultaneously? Can we train influence distributions or influence predictors for each of them, and then run them in parallel? And well, the first issue we find with this is that if we do simultaneous learning, if we train them in parallel in the different simulators, this is the same Bayesian dynamic network that we had before, but now we see that part of the non-local state variables are the actions of the other agents. So in this case, we just have one agent, J, but But in the case of the traffic scenario, you will have 24 non-local state variables that are the actions of the other agents. And as soon as they change their policies, they will also change the distribution of the influence sources with respect to the local state action history, because they're going to affect these influence sources, and these influence sources are going to affect our local region. So in principle, we cannot really train our agents in parallel, because the influence distributions are no longer stationary when the agents learn simultaneously. So this distribution here, maybe we train it at the beginning, and then as soon as we update the policy of just a single agent, then this distribution is useless, because now this new agent that changes policy is gonna influence my local region in a different way. And then we asked ourselves, is this that bad? Like, I mean, in general, this is the case, but is this that bad in all problems? And so we make two observations that we sort of analyze theoretically. The first one is that multiple joint policies might induce the same influence distribution. So what I mean by this is that you could have many different policies that are affecting your local regions in the same way. So this proposition here, this result shows that the space of joint policies is always greater or equal to the space of joint influences. And in the stream case, when the regions are independent from one another, there's just one influence distribution for each agent, and there could be when there could be many, an infinite number of policies. So in most environments, you will be somewhere in between, where two policies or three policies map into the same influence distribution. So this is the first observation, and the second observation is that multiple influence distributions may induce the same optimal policy. And I'm not going to go through the details of this result, but essentially what we show is that the closer the influence distributions are to one another. So you can imagine that at the beginning I train my influence distributions, and then I start updating the policies. When I update the policies of the other agents, the influence distributions are going to start deviating from one another. So the true influence distribution and the influence distribution that I trained are going to start deviating from one another. But it might be okay to leave this, to let them deviate, because the optimal policy that I'll get will still be the same. Is this clear? Okay, I assume it is. Okay. So then what we have, like, and this is the algorithm that we came up with, is just very simple. Rather than having to update our influence distribution every time we make a change to any of the agent's policies, we are gonna do only updates every certain number of time steps. So we first train our influence distributions for each of the agents, and then we start training our agents, we start training our policies, and only after F time steps, we will update our influence distributions again. And we can do this because, one, many influence distributions may induce the same optimal policy, and two, many policies may induce the same influence distribution. Okay. So now I'm going to talk about some further observations that we made that are a bit more experimental. We don't have a theoretical analysis for those, but the results are quite conclusive. And so we came up with this hypothesis after seeing the results. So on the left, I have the global simulator, and on the right, I have the influence augmented local simulator. And when we train agents on a global simulator or on an environment, and we train them simultaneously, well, you all know that the transition dynamics from the perspective of every agent start to look non-stationary. And the reason for this is that the other agents are updating their policies, so they are affecting your transitions differently, and this is bad for convergence. In our case, as long as we don't update our influence distribution, we will have a transition dynamics that are stationary but biased, right? So we're giving away this accuracy of like the distribution for a more consistent signal that we can rely on to learn. Another reason why the influence augmented local simulators, the distributed influence augmented local simulators may be good for simultaneous learning is that the stochastic gradient updates that we perform on the policies may lead to policies that are worse than the previous ones, and the agents may try to adapt to these poor performing policies, and this is just because of the inherent stochasticity of the learning process. However, in our case, we can decide to only update our approximate influence predictors when we know that the other agents' policies have improved sufficiently. So essentially, what I'm saying is that during the learning process in a global simulator or in the environment, you will have many points in time where you may not want your agent to adapt to another agent because this other agent is just doing random stuff that doesn't make much sense. So you don't want to adapt to this poor performing policies. And the last observation is that you also before you can improve, you also need to take exploratory actions, and exploration and cooperation don't go very well with each other, because an agent that is exploring is an agent that doesn't really want to cooperate, or that is not thinking about cooperating. It's basically just trying to figure out how to perform well by itself, maybe with others, but you know. And we also solve this issue by deciding when to update our approximate influence predictors. So we only update them when we know that the policies have improved sufficiently. Okay, these are again hypotheses to explain the results that I'll show now. So what we have here is again the same baselines as before. Have the global simulator, the untrained distributed influence augmented simulator, which is the distributed influence augmented local simulator with untrained approximate influence predictors, and the trained distributed influence augmented local simulators. And here the frequency of training this approximate influence predictors is 1 million time steps. So we see here that not only green is faster, but also it performs better than when training in the global simulator, which is a bit counterintuitive because the global simulator is more exact. So this is why I gave I made all these observations to suggest that training in this particular scheme might be actually beneficial for the agents. So we see that the global simulator, when we train policies on the global simulator, they have issues converging. What else do we want to say here? Well, so this is for the 4 agent scenarios or 4 intersections. We trained 25 intersections, 49, and 100 intersections. I'll show a video later of the 100 intersection environment. Okay, any questions so far?
Would you mind going back one slide?
Yeah.
So the dynamics, they are stationary conditioning on the influence variables, right? And then the AIPs are the ones that produces the variables. Mm-hmm. So my question is, how accurate do the AIPs actually have to be for the first I guess observation to really hold.
Yeah, so that's what I was going to show here, actually. So here is a comparison of different training frequencies for the AIPs, for the approximate influence predictors. So we have like 4 million is just we train it at the beginning and then we stop. We don't train it anymore. And this is the purple curve. And you see that the agent here doesn't get to perform that well. The training finishes faster. So when you see this dotted line, this means like the training has finished, and we just extend the line so that we can compare. So it trains much faster, but because it never updates the approximate influence predictors, then this influence distribution, the true influence distribution, is very far from the approximate influence distribution, which is what we see in this plot on the right. The influence loss starts increasing as we start training the other agents, because now the influence changes, the influence that the agent receives, and this is the average over all the agents. So we have an approximate influence predictor for each agent. Here there were 25, so this is the average over the 25. Whereas when we update them more often, then we can reduce that loss. So all these drops that we see here correspond to the times or the frequencies at which we update the approximate influence predictor. So you see that like with 1 million, with a frequency of 1 million, it's more than enough, and then you need to update it more frequently. Updating it more frequently doesn't seem to be that bad in this case, but it just takes longer. Whereas in this scenario, for instance, updating it very frequently is actually detrimental, which suggests that our observations from before are actually true, because what we see is that when we update this influence distribution too often, we are getting worse performance than when we did it less frequently. And in fact, in this environment, this is a warehouse environment similar to the traffic domain, similar structure, not similar environment. It's sufficient to update the model just once. So that means that the same influence distribution that we trained at the beginning gives us the same optimal policies, or not optimal, same policies after training. So yeah, I hope that answers your question, right? Like
yeah, it does. Yeah.
Here we see that an influence distribution that is actually very far off from the true distribution is actually sufficient. And the reason we see here that it's actually decreasing is not because we are training it or anything. It's just because the environment becomes more predictable. The influence sources become more predictable as we update our agents. So the entropy in the cross entropy, the entropy term, just decreases. I think so. This is the video that I wanted to show. This is agents trained on the distributed influence augmented local simulator, but we test them on the global simulator. So yeah, this is just to show how big it is. And well, by the way, so training this on the 100 intersection takes just about 6 hours with dials. It takes about I believe like almost 11 days with the global simulator. So the computational speed up is also important. Wait, how will we go back? Okay. So yeah, so this is the end of my talk. Thank you very much for listening. And yeah, if you have any questions, then you can ask them now, or you can email me. Happy to discuss further after the talk.
Thanks so much for the talk. Yeah, I guess if anyone has questions, we have about 10 minutes, so quite a while to discuss. I'll mute myself, but I do have a bunch of questions.
I have a question on the space complexity of the AIPs. So like, how does it scale with the number of sub-environments, or like, with the number of environments that you divide up to? Like, let's say you divide into 4, then does each individual environment need like 3 AIPs for the other 3 sub-environments?
No, you just need one AIP independently of like how many environments you have. So each simulator has an AIP, and it doesn't matter how many. So in the case of the traffic scenario, it doesn't matter how many intersections you add, you will still have the same AIPs because they're basically predicting the influence sources, and the influence sources do not change, right?
Yeah.
You said you have more influence augmented local simulators, so you have to add for every agent or every local region that you add, you need to add another influence augmented local simulator, which is a local simulator and the AIP.
Okay.
Yeah.
Okay. So I guess the question I had earlier about treating all multi-agent problems this way is, like if we think about like SMAC, the agents are fairly loosely coupled to each other. Do you think that this method would work for instead, just learning a model, a rough model of your interaction with other agents, doing all your simulation inside that fast model, and then, have you looked into this at all? Do you have any thoughts on?
No. So we started to think about how we could capture the influences in more, let's say, less structured environment, because we do agree with you that the interactions with other agents are not, so the agents are not that coupled to one another. So we started to look at things like attention, whether we could have some model that will sample influence sources and then predict them. I think it's a bit hard. What you can do though is like when you're if you're doing some sort of opponent modeling, then if you had some sort of graph that you could use to know what opponent is influencing you at what point, then you could basically forget about most of the opponents if you know which ones are connected directly to your agent. So in that sense, like, that's probably the easiest way of applying this sort of idea, this framework.
Well, let me go one step further, and I'm curious. So like, another option is to try to force the agents to behave in such a way that the subsequent graph is amenable to this type of factorization, right? Like, I mean, it's a prior.
Yeah,
but
I see what you mean. So that this is like, so you're trying to make the agents aware of like their interactions with other agents and not letting them, let's say, move such that these interactions still so that the interactions are still the same in some way.
It's kind of a coupling between the agent behavior and the model learning process. It's not obvious to me how to do such a thing.
So I'm thinking about a swarm maybe of like helicopters or something. And then these are somewhat restricted, their policies are somewhat restricted, so they have always to be next to a particular set of neighbors. So that might work actually. So some of the things that we were thinking about is as well is like, how do I do it such that can I create a policy such that the influence that I receive from the environment is the least, right? Like how can I make it so that I can only care about my local region without having to really wonder about what the others are doing. So you can think of this as like I decide to self-isolate myself in a room because I'm afraid of the external world, but I do my stuff in the room, and I compute a policy there, and I can do just fine without having to interact with the others. So this is another.
Yeah, this is kind of what I was getting at, right? Like, how can you force a policy to choose to interact with like one agent instead of all of them in such a way that now your model learning component can be pretty good,
right? And this is something we do as humans, right? Like we try not to interact with too many people. Or, well, I don't know if that's true, but yeah.
But I mean, we do try to factor our cooperation in some way, right?
Yeah.
Like I don't try to do a collaboration with all 40 individuals at once.
Right.
Yeah, so there's this kind of coupling between the model learning and the
right.
and the way you choose to behave, such that model learning is easy. Yeah, I think this was really great work. I was psyched when I saw it. Got into
I was very happy when you sent me the message, to be honest, because like it's kind of hard to get attention from other people, especially coming from a small lab. So then the paper got published and everything, but your message really meant a lot. So thank you for that.
Oh, yeah. I mean, you are probably among the small group of people who have also tried to train the 100 traffic light simulator.
Right.
So
yeah. It was not that hard, I have to say. Once you have like once I had the single agent, it's just a matter of like compute.
Yeah.
But yeah.
I'm gonna mute myself so someone else can ask a question. But yeah, great work.
Yeah, thank you so much. Yeah.
Quick question. What is the simulator being used here?
Sumo. So it's
Sumo.
it's a simulator built in C++, but you have this nice wrapper that Eugene worked on. It's from Berkeley. Are they still actually actively developing?
All of the developers have graduated.
Okay.
So we don't. Everyone has private forks of it. They develop it, but the main project is no longer under active development.
Right. I also have my private fork, so yeah.
Yeah. So okay. So the other question I had was, do you have the sense that like, so you're learning these local simulators and you discussed there's this decoupling of the local reward from the global reward. And yeah, do you think that like, do you see any evidence that is causing non-cooperative behavior? Do you have any sense about whether non-cooperative behavior is emerging here as a consequence of that?
Oh, we haven't checked that, but yeah, that's a good question. We should definitely investigate that.
And the follow-up question is, have you thought about any ways of kind of coupling the like making the agents cognizant of their influence on other people's models and on the model learning?
Yeah, so that's what I was getting at before. Like you could potentially do the same you do with the transitions, but with the rewards. You could create, you could have your base reward, your local reward, and then on top of that, you could learn some delta that tells you what's the effect of your actions on the global system, like what reward you get, and that actually might be beneficial for credit assignment. I think there are a few works that have investigated this already, but yeah, I cannot tell from the top of my head. But yeah, so one paper I like a lot is this paper contrasting centralized and decentralized critics. It got the best paper award at AMAS last year.
we had Chris present that paper
a
couple months ago.
Yeah, so so in that paper, they show that like having the local reward is actually enough in terms of not the local reward, it was the local value function, but for the discussion is sort of the same thing, right?
Yeah, I mean, that paper has one key restriction, which is it assumes convergence.
Right.
Right. Those value functions are equivalent at convergence, but
Right.
not before that. So
no, yeah. So yeah, they do mention that though, right?
No, they don't obscure that fact at all.
No.
I just meant that, like,
yeah.
I still don't know how to think about the results of that paper, because maybe the behavior away from convergence is the thing that really matters.
True. So that you're saying, like, basically before you've converged, you may get better values or more accurate values because you're adding the actions of the other agents. Yeah, I agree. I agree with that. At the same time, I think, like, having that extra bit of information might increase the variance. So there's another paper from Thomas Spooner. He was at JP Morgan research here in London, which shows that when you have global value functions, then you get more variance in your value estimates, and then it's much harder to actually converge.
If you could share that in the Slack channel, that'd be awesome. Maybe we can have him come present. I have to run, but thank you so much for the talk. It was really great.
I don't think I'm in the Slack channel, but
I will send you an invite to it.
Okay.
We added you to the group, but we didn't add the Slack channel invite to the message yet, which is our bad. I'll send you an invite.
All right, perfect. All right, thank you so much.
All right, thanks again for coming.
Bye.
Thank you.